Now we're going to perform nearest neighbor declustering. We also need the nearest neighbor estimate for validation purposes. We can always calculate the clustering weights from any of the estimators by accumulating the weights that were given to the data for each cell node. Because we are producing an estimate and therefore a column in our block model, we need to specify the column name for that estimate. In our case, the nearest neighbor estimate is just another column for gold. Therefore, we use the original gold variable and we clone it with a new column name and we call it AU_NN. So now, whenever in our model we have a column name AU_NN, that's going to be treated the same as the gold. So if we are plotting AU_NN, it will have the same color, the same limits, the same looks as the original gold variable. So let's see how we generate an estimate and at the same time keep the declustering weights. Let's run this first and then I will explain what this cell is doing. The estimation is complete. So let's see what we just did. In the first line, we initialize the nearest neighbor gold column as all missing number or not a number. We iterate over the domains we want to estimate at. We build a search for the estimation based on the variogram. This search is built using the rmsb.search.fromVarioBuffer. This function will create a search based on the variogram ranges and anisotropy. It's going to select the threshold, which is the buffer at. So at the 90% of the cell, we are looking at what the ranges are, and then we buffer those ranges by a buffer value. So in our case, we're selecting the variogram for the given domain. We are buffering at the 90% of the cell by 5 times that range. We are defining the minimum number of composites to be 1 and the maximum number of composites to be 1. Because we are just doing nearest neighbor, we only need to find what is the nearest composite to each block in a block model. Next, we initialize the nearest neighbor estimator, and this estimator only requires the search. With that estimator, we move into a estimation step. All estimators in RMSB will have the .estimate method for estimating. We are selecting the indices of the blocks for this domain, which we previously stored on this grid_indexes, so that we only estimate the selected blocks with the soft composites for the selected domain using the gold data. Because we are only interested in the array, not the grid or data frame format, we specified that copy meta is equals false. If copy meta is equals false, the output of this function is arrays. If copy meta is equals to true, then the output of this function is the same as the grid object. And then, because we are interested in keeping the declustering weights, during the .estimate call, we must define accumulate weights to be equals true. When we define this to be equals true, during the estimation process, all weights that are given to a given composite is stored for that composite. The result of the estimate function is the estimated values for the nearest neighbor, which we store in the nearest neighbor column of our grid. After the estimation, the weights should be available in the estimator itself. So we can use estimator.weights, And the result of this function is an array with the weights for the nearest neighbor. In the final line, we just make sure that every cell of the grid has been estimated. That means there's not a number left in the grid. So if we look now, the grid, we should have the nearest neighbor estimate. And if we look at our composites, we should now have both the cell declustering weight and also the nearest neighbor weight. To finalize, we make a visual check of the nearest neighbor estimate that we just performed. For that visual check, we use the parse.main section. We have seen this function previously, so I'm not going to explain. It just generates a cross-section that's consistent throughout the workflow. So this plan view section shows all our composites, the shell shape, and the estimated blocks with the nearest neighbor. Another common type of validation model is the inverse distance. And we are also interested in the inverse distance weights to compare. So we are going to do a very similar procedure to what we just did with the nearest neighbor, but for the inverse distance. We start with cloning the variable so that any column that is called AU underscore ID.2 will be considered to be the same as our original gold column. We initialize the values with not a number. We iterate over the domains. We create a very similar search to what we've done for nearest neighbor, but this time we increase the maximum number of composites. We initialize the inverse distance estimator. In this case, it takes a search, and also we need to specify the power. We're using a power of 2. We select the locations of the grid that has the domain we are estimating, and we call the estimator.estimate. Very similar call to what we've done for the nearest neighbor. We specify the locations that we want to estimate, which are the indices related to the domain. We're using the soft composites for that domain, gold variable. We are only interested in the array output, and we want to accumulate the weights in estimator. The result of this estimate call is stored in the grid in the column we just created for the inverse distance result. Next, we make sure we store the inverse distance weights using the same function, estimator.get cumulative weights. And at the end, we just make sure that every grid node got an estimated value and there's not a number left in the grid. Just as we did for the nearest neighbor, we're going to take a look at the plan view section for the inverse distance estimation. So we can see our composites, the shell shape, and the estimated block.